So I have an apology to make. My name is not Richard Yarnall. I am Mark Newberry. Richard is poorly, so I have stood in for him. So excuse me if I seem a little bit light on knowledge tonight, but I should be sufficient for the 30 minutes that we have. So today, in 30 minutes, I will cover the different switch types that you can design, the typical feature sets that you require in the mid and the high range of switches. That is precision time and redundancy within the switching network, and how you achieve scalability and implement the scalability, how you design your product faster, get to market faster, get to revenue faster, and also design for portability. So, without further ado, I'll move on, and I'll stand over here where my notes are. So, switch types. So, have we all had an unmanaged switch on our desk at some point in the past when you're doing some development on TCP/IP? Generally, plastic housing, probably from Amazon for 10 to 15 pounds. To design one of those, it really is just silicon, hardware design. There's no or very little software. The functionality is inherent in the silicon. It is just packet forwarding. There's no decision making. There's no security generally. Very little improved functionality, but you can do the design in maybe a day. EMC, etc. takes a lot longer, but it's very fast time to market, and primarily a hardware development. Great, really, for audio applications where you want to create an audio switch and sell it for lots of money with very little added benefit. We then move on to the lightly managed switches. These have more functionality, so you may get VLANs, so be able to run private LANs effectively over the public network that you are creating. These could run bare metal. They could have a Linux distribution with switchdev, or they could have another OS. They could be configured via a command line CLI, command line interface, or a GUI. Some amount of port-based security, so coming back to the VLAN. And they might have a GUI or simple network management protocol for monitoring and configuration. Generally, these are medium cost to implement, and time to market really depends on the complexity. So, lightly managed solution. Linux switchdev, all bare metal. Switchdev is powerful and well featured. If you've used OpenWRT, their DSA architecture is now based on switchdev. And if you want precision time, then we can add a PTP4L package to switchdev, which has that feature and doesn't need a GUI. And generally, on the right-hand side of the screen there, you can see some commands to bring up each interface and add it to the bridge. Or I should say add it to the bridge. Create the bridge, add it to the bridge, and then set the IP link. All right, yeah. So you probably do have a CPU on this. There is a bridge and there is each port. So that's the lightly managed switch. So, fully managed. Richard has called this a pizza box. Now, I moved to a managed switch at my home, actually, because I had a faulty network cable. And actually, having a managed switch there, I could detect what faults there were on my 25 meters of cabling that I had out to my outside office, and just see when it failed, because generally, actually, it was moisture ingress in the cable. But it does, managed switches do give you a lot of features that are beneficial. So, but in this instance, Microchip as a customer, as a vendor, are really offering you unmanaged switches, lightly managed switches, and fully managed switch silicon. And we also offer the software, the OS that goes with them. So what you need for a fully managed switch is a precision time protocol, so time-based traffic switch, time-based traffic shaping as well, which I'll come on to later. VLANs, quality of service, prioritization, preemption, aggregation, redundancy. So redundancy, MRP and FRARE is something that I'll come on to later. A lot of the switches are Linux or other OS based, so that might be pfSense based or Linux. And there's a performance balance between the on-chip peripherals and the host MCU, and the ability to do protocol offload to hardware. There's also, in a fully managed switch, there's support for multiple management protocols. And again, GUI or the simple network management protocol for monitoring and configuration, and command line interface as well. This has a much higher cost of implementation, longer time to market, hardware and layout likely to be faster to develop than the software. So generally, with a fully managed switch, the hardware doesn't take that much longer to design than a unmanaged switch, but it's the software that takes a very long time to develop. When I'll come on to a reason for choosing Microchip for switch development later with the software. So here we can see the fully managed implementation with modules. So priority flow control, mirroring, link aggregation, IGMP, spanning tree, etc., etc. So we do provide free-to-use software modules, documentation for use with Linux. The switch dev approach does require integration, but that's reasonably seamless. And how, basically, really, it comes down to how will the switch be configured. Is that in hardware? Is that in a web GUI or command line interface? So, in a fully managed switch, timing profiles. So running top to bottom, IEEE 1588 PTP. It's a basic time protocol. It's very common, and not all devices need to support PTP. We don't run it generally on consumer networks, but on industrial networks you may. 802.1 AS GPTP is a superset used in automotive and AV applications. It's more robust against delay variations, as all devices on the network must support timestamping. It's got much better performance than 1588. We then move on to telecoms profile, so ITU TG8265.1, so frequency profile, and then the 8275.1 time and phase profile. So I'll come to a slide later that shows the much better performance with the Synchy DFPLL, I think it is, that's used on the 8275.1. So now running top to bottom with G8275 being the most advanced protocol here. So this can provide less than 1 nanosecond timing accuracy. It's brilliant. And the 802.11 AS, this is sort of 10 nanoseconds timing accuracy. And the reason for getting timing accuracy on switches is really to make sure that the network, so you can benchmark the network, so you can benchmark financial transactions, so you can see the order of a sequence of events on the network. There's also a note here that clocks can degrade, and when you're designing a network, and we'll come onto a holistic approach of a network on a slide or two, consider a mix of the G8275.1 with PTP. So here we can see the effects of timing accuracy. So top right is 10 nanosecond jitter there on the PTP. And then on the bottom right, we can see a sort of 1 nanosecond jitter running G8275.1 PTP. So that is timestamping, on the packets. So if you need the timing accuracy, then you need those extra protocols on there. And this is some of Richard's development equipment that he has for developing these slides. How are we doing for time? Good. So time-aware shaping. So this is another advanced feature of switches that are used in industry. So this is all about scheduling time slots for specific data types. So you may have 2 sets of data coming into a switch, high priority and low priority. The network in the middle there must be time-aware. And then at the other end, that data has to come out with high priority and low priority in the right order. So here, this shows time-aware scheduling with frame preemption. So on the top right image there, we've got a blue frame, interfering frame it's called. And that means, because that frame is on the wire at the same time as we're trying to, or before, trying to transmit the 5 yellow-orange frames, the 2 last orange frames are delayed, so they're out of spec with the protocol. But because on the 2nd and 3rd and 4th, we're then using different techniques to preempt that interfering frame. So either send it before the time that the 5 other frames need to be delivered, or splitting it so that that blue interfering frame is split into part 1 and then part 2, either side of the 5 frames that do need the scheduled time. Right, I am halfway through my slides and 10 minutes in, so I think I'm doing okay. Right, ring redundancy. So, I can't make this interactive, which is very annoying. But I would at this point, I'll say, why do we need ring redundancy? And someone would say, a clever answer. Generally, we need ring redundancy because in industrial applications, if you've got some plant and equipment, you don't want a link to bring down your factory automation system, your robotics, etc., etc. So in this slide deck, there's two styles of ring redundancy covered. MRP, Media Redundancy Protocol. So as you can see from the right-hand side of the image here and the bottom left, this is effectively a ring of devices. So data is transmitted in both directions around that ring. So you do have differing roles within the system. You've got the Media Redundancy Manager, MRM. You've got the Media Redundancy Client, MRC. And then you've got an Auto Manager, an Interconnection Manager, an Interconnect Client. And it does take 10 milliseconds to recover time with the Microchip solution. And we can also support multiple interconnected rings. So on the right-hand side there, you can see two rings separated by almost a parallel ladder, which actually brings me onto the Freya implementation, which is the frame replication and elimination for reliability. Rolls off the tongue very seamlessly and is IEEE 802.1CB-2017. So it reduces the probability of packet loss by replicating packets at their source. It transmits these packets over multiple paths, typically a ladder type configuration, and finally removes duplicate packets at the destination. It does allow for mesh networks. It supports and maintains TSN networks, time-sensitive networks seamlessly, and provides zero recovery time. It does, however, require dedicated switch hardware to implement. So what we're talking about here, really, for switch development is very high-end silicon, provides a lot of features, and takes a lot of software resource to get it going. But we alleviate some of the software resource for getting this going by providing an image effectively for them that you can customize with your own graphics and customizations. So Freya, the frame replication and elimination for reliability, is not currently supported in mainline Linux, but we do provide a dedicated tool for Linux. So Freya requires all participants to be Freya aware. Freya networks comprise of the N system, the ES. This contains talkers and listeners. Maybe endpoints such as cameras, sensors, drives, actuators. So we're talking about A and B in the diagram, either side of the central blue box. We then have a relay system, which is the blue box. And this acts as a gateway between N systems and the redundant networks S1 to S4. I think this next point has got an error, but I wasn't going to bring it up with Richard. S1 and S2 are also known as red boxes. I think he means S2 and S3 possibly, which link between redundant and non-redundant networks. So that's really the redundancy within the networks, the two modes that are quite simple to explain. What I'll move on to now is scalability and talk about software, because software takes time. We can, the hardware is one thing, getting that designed is one thing, getting it manufactured is another thing. We then need to run some software on a fully managed switch. And really this falls into a triangle type arrangement where you can spend lots of time and have lots of features, cost you lots of money. You can do it in low time and low budget, but have no features, etc., etc. So different applications have different requirements. So here we can see there's EtherCAT, there's some remote I/O, there's a real-time engine for barcode scanning, etc. There's some multi-axis drives. There's some endpoints on the right-hand side. There's some time-sensitive networking on the right-hand side. There's different ring speeds, so 1 gigabit per second, 10 gigabit per second, possibly TSN with Freya, and a HSR ring as well in the bottom center. So quite often there's multiple switches for multiple applications that you need to design for: low speed, high speed, low features, high feature set. So to design the software, we have got 3 software stacks. So I'll start at the bottom of this table. So we've got web stacks, which allows for basic level 2 management, so things like the VLANs. We've got SMB stacks, which allows for that basic level 2 management, but also advanced level 2 plus management. Now, I'll be honest, Richard would know what the features are of those. Unfortunately, I don't. And then we have the iStacks, which gives you the industrial and TSN features, which is really fully featured. So all of this software stacks, 20 plus man years in development time. We do issue quarterly updates for those. They are single license per organization. They are scalable, so you can be deployed on small to large switch platforms on a single license. What these allow you to do is basically develop a commercial grade switch in weeks, not years, effectively. They are fully customizable, so you can add and remove features or add and remove the GUI, skin the GUI to your liking. And a single license covers a wide range of end products. So we have here the iStacks Advanced Feature Support Matrix. So you can have per stream filtering, effectively domain protection features, high traffic availability features, time distribution features, and also management features. So this is some images of the fully managed switch interface here. So you can see on the left-hand side, it looks like many of your routers and switch interfaces that you'll have seen. So this is branded as Microchip, but we can do whatever you like. We have 1 PPS outputs for time synchronization as well. We've got 8 to 16 ports, 24 ports with SFP in there as well. You can turn on green Ethernet features, the low power features of the Ethernet if you're running on short cabling. Media redundancy, link redundancy, DHCP, V4, V6, time protocol, VLANs. Lots and lots of features are built into this, and it's just a licensing for you. So again, actually, that's one of the bigger switches configurations there. Yeah, so I'm just going to see where we are in the slides. Perfect. So this is where we're sort of looking at the portfolio of parts. So I'll start at the bottom. So we've got 4 1 gigabit time-sensitive networking switch, so 10, 100, 1000 meg ports with a real-time engine. So that will support things like Profinet and OPC UA. We then move up a level to the 8 ports DIN rail switch, or to be honest, the form factor can be whatever you like. We then move up to 10 ports. So this is where we add 28 gig TSN switching with 8 1 gig ports and 2 10 gig ports. Moving up another level, we then move to the 64 gig TSN switch. So that's 24 1 gig ports and 4 10 gig ports. This supports iStacks, and it can have 1, 2.5, 5, and 10 gigabit Ethernet. And then at the very top, 64 ports, 200 gig, and there we have a combination of 1, 2, 2.5, 5, 10, 25 gigabit Ethernet. So that's really the product portfolio that we're targeting. There are more parts in development. There are more parts in concept. That's all under NDA. That's all things that if you want to know more, then please talk to us. Yeah. There is an option for questions. Does anyone have any questions, and we can try and arrange a microphone? I don't think so. Okay, well, thank you. Oh, we do. Apparently I need a headset as well to hear what you say.
Hello.
Yeah.
My name is Pawan Patel, and I have a question on what's that 200G TSN time sensitive network? Is it are you guys making a 200G switch?
No, it is a 200 gig total throughput.
Okay.
And each port will either be 1, 2.5, 5, 10, or 25. But 200 gig throughput in total.
Okay. So it's like 25 cross 8, like
Yeah.
that way.
Yeah. That's how the 200's worked out. Yeah. Good question. Any others? Well, thank you very much. I have not been Richard Yarnall, but I hope you have found this enlightening. You've been a good audience, so thank you very much. Perfect. Thank you very much.